Yeah, sure. We can.
So you can. Okay, great. So first of all, thank you very much for the kind invitation. It is a pleasure for me to give a lecture here in this online workshop. So ideally, I would give kind of a lecture in the Blackboard, but since this is an online event, I found the next best thing, I think, which is to kind of make handwritten discussions. So which I hope will be easy for everyone to follow. But if there is some technical issues, so if there are some parts that are not very clear, please let me know. Okay. So so this lecture will be about shadows of black holes. So essentially, the shadow is the image of a black hole, and you can wonder, since classically. So let me write that down. So since classically, a black hole does not emit radiation, then you can ask, how can we see? Can we actually see a black hole? So if there is some background light, so, and this will happen a lot in some astrophysical scenarios. So if there is some background light, so this light can come typically from an accretion disk, then this will provide some contrast, like some contrasting light. So this will provide some contrast. And essentially, if you have this background light that provides contrast, and you have a black hole in the middle of this region, the black hole will create a region of your sky that has a sharp decrease in luminosity. So schematically, the situation will be as follows. So you have a black hole. So this is the black hole. And you have some kind of very hot gas, some accretion flow. So this is some accretion flow around the black hole. And it is emitting radiation, electromagnetic radiation. And if you take a picture of this, so in the picture you have two observation angles, say this vertical axis in the image is angle 2, and this one is angle 1, okay? You would observe some dark region in the image corresponding to the actual image of the black hole. So let me just put that down. So this is the image. If you take a section here with a constant angle, angle 2, for example, angle 2 equals constant, and you represent the luminosity along this line, you would get a plot that would look something like this. So this would be angle 1. This is the luminosity. You'd have something like this, and then you have kind of a sharp decrease. And this region here, that would correspond to this area here in the middle, where you have a sharp decrease in luminosity, this would be more or less the shadow of the black hole. Later on, I will give a more precise definition of what I mean by the shadow of a black hole, but for the moment, this suffices. So notice that luminosity here is not 0 exactly, because often there could be radiation being emitted directly in front of the black hole. So the luminosity in the shadow doesn't have to be exactly 0, but typically you would expect to see a sharp decrease in luminosity because of the presence of the black hole. So the thing is that the emission from the accretion flow it is, of course, model dependent on the physics of the accretion and several factors, also the temperature and so on. But in contrast, what's interesting about the shadow, I would say, in contrast, the shadow, in particular, the shadow edge, should only depend on the space-time geometry close to the black hole. So in that respect, the shadow, and in particular the edge, so the edge here, the border of the shadow in the image, works kind of a probe of the strong gravity regime. But let me emphasize two things. The shadow, and in particular the shadow edge, is not an image of the horizon, but actually a measure of the properties of what is called in the literature spherical photon orbits, which I will give a brief introduction in a moment. So this will be for the Kerr black hole, although there is kind of a generalization outside of Kerr. So just let me emphasize that the actual image of the black hole, the shadow, is not an actual image of the horizon, but of something else, of a set of bound null orbits of null geodesics. So for the purposes of this lecture, so in the 1 hour periods, I have to condense a lot of information, but in order to optimize the knowledge that you can obtain, I'm going to focus mainly on the Kerr spacetime, although there are some properties that can be generalized to other spacetimes as well, although not all. So we'll mainly focus on the Kerr spacetime. So, of course, I'm going to assume that everyone present now have heard about the Kerr metric, but so that everyone is on the same page, let me just give a very brief review. Not only just to give kind of so that we are on the same page, also on the notation of the coordinates that I'm using. So, what's one of the interesting properties about the Kerr spacetime? It is there is a series of uniqueness theorems that establish that Kerr is the only stationary, regular, on and outside the horizon, asymptotically flat, black hole solution in vacuum general relativity, in vacuum GR. So because of this, because of these uniqueness theorems, there is, of course, great potential for astrophysical relevance. Of course, this does not prove necessarily that all black holes that would exist in the universe are Kerr, necessarily, because a theorem is only as strong as its assumptions, as it's often said. And you can notice that there are several assumptions. You assume stationarity, you assume some sort of regularity, regularity of the geometry. I'm not talking about regularity inside the black hole, only regularity of the geometry on and outside the horizon, also asymptotic flatness, and also vacuum. You can have some geometry that is not, that has some matter fields, and this might be a way to go around these theorems, and also general relativity. So, but despite this, the Kerr solution is, of course, very well motivated for astrophysical applications. So in terms of the metric, let me just write that down very quickly. So in Borel-Lindquist coordinates, it looks something like this. Okay, so the t coordinate is kind of a time coordinate, phi is kind of an azimuthal coordinate, and then you have a kind of radial and theta coordinates. So these Borel-Lindquist coordinates, and this rho squared is r squared plus a squared cosine of square theta, and delta is r squared minus 2mr plus a squared. So just a couple of key points here. You have this metric depends only on two parameters. So the parameter A, which is the spin parameter. So it kind of embodies the rotation of the black hole. So this describes a rotating black hole in vacuum, general relativity, where A represents the spin. As you probably know, there is a maximum spin allowed. And then you have M, which is the mass of the black hole. And one interesting thing here is that the metric does not depend on either the t coordinate or the phi coordinate. And so the metric is axisymmetric and stationary and possesses stationarity. And this will be important for having conserved constants of geodesic motion that will be important later. Okay. So in terms of the electromagnetic or radiation, we shall consider only the high frequency limit of radiation, so of electromagnetic radiation. So in the high frequency limit, which will be assumed, the wavefront of the electromagnetic radiation is well described by the motion of null geodesics in the space-time. So essentially, the motion of light rays as null geodesics. This will probably not be news to you. So the Hamiltonian, let's start with the Hamiltonian of the null geodesic flow. Depends on the coordinates and the form momentum of the photons. This will be 1/2 g mu nu p mu p nu, where this p is just the form momentum of the photon. Okay. This for photons will actually be zero. Would be proportional to the mass of the particle, and for the case of photons, this will simply be zero. So Hamilton, you can obtain the actual equations for the motion, the general ones, using Hamilton's equations. So you take so here the dot signifies a derivative with respect to an affine parameter along the geodesic, okay? And now you can notice something, like I mentioned for the Kerr spacetime, and actually this part is valid for any spacetime that is stationary and axially symmetric in the sense that it possesses, so let me write that down. So it's stationary, a spacetime which is stationary, so you have a Killing vector field delta t, so this is a Killing vector field. Then dh by dt will be zero because the metric does not depend on the time coordinate. This will be zero, and because of this first Hamilton's equation, then this implies that pt dot will be zero, and so pt is a constant. You can actually say that it's minus E, where E is the energy of the photon. Similarly, because of axisymmetry, this is valid for Kerr, but not only. So also the delta phi is a Killing vector. So dh by d phi is zero, and likewise, this implies that p phi is a constant of geodesic motion. Let's call that L. Okay, this will be the angular momentum of the photon. the axial angular momentum of the photon. Now, for photons in particular, we can actually it will be important to define some impactor parameters and to redefine this energy to be 1. You can always do this in principle because you can rescale the affine parameter along the geodesic such that E is equal to 1. So you can kind of reabsorb that by redefining some of the other quantities. So this is not a problem. We are keeping the generality. Let me also mention that if you take the derivative, total derivative of the Hamiltonian with respect to the affine parameter, so this lambda is the affine parameter along the geodesic. So since h depends on x and p, I can take the partial derivatives. Whoops. And now plugging into the Hamilton's equations again, this will be minus p mu x dot mu plus x dot mu p dot mu. So these two cancel, and so this is 0. So dh by d lambda is 0 along the motion of the geodesic, which implies that h is a constant and will actually be generically equal to minus the mass of the particle squared over 2, but since this is for photons, this is equal to 0 for photons. Like I mentioned, the Hamiltonian will be equal to 0 in this case. But it's also a conserved quantity along the geodesic motion. So as a summary, there are at this moment, there are 3 constants of geodesic motion, but you have 4 coordinates in total. So you have the time coordinate, radial coordinate, latitude coordinate, and the azimuthal coordinate. And this is not enough for a full integration of the geodesic motion because you have less constants of motion than coordinates. And generically, for a space-time that has these 2 killing vector fields, these will be generally the case. And if you want to obtain the shadow of a black hole, typically you have to integrate null geodesics numerically, ideally taking advantage of these conserved quantities of geodesic motion to simplify the equations that you have to use. But regardless, this is the best you can do. In the case of Kerr, you can take one step further because in the case of Kerr, there is a hidden symmetry, a symmetry which is not obvious at first. And there is actually a 4th constant of motion. In addition to these previous 3 ones, there is a 4th constant of motion. Let's call it capital Q. And it was discovered by a gentleman of name Brandon Carter using the Hamilton-Jacobi equation, Hamilton-Jacobi formalism. This is a very interesting discussion, but in the time span of 1 hour, I don't have enough time to cover how the deduction of this and so on, but it's very interesting. So this 4th constant of motion is usually dubbed Carter constant in name of the Brandon Carter. And if you use the Hamilton-Jacobi formalism, you can write some equations of motion for the null geodesic motion around Kerr. So for the radial equation, you have rho squared r dot. So this is a 1st order equation plus minus then the square root of a function capital R. Okay, that I will define in a moment. You have rho squared theta dot, then plus minus square root of capital theta of theta, and then you have theta dot, which will be the for momentum with index above, and this will simply be GTT PT plus GTT P phi. And if you recall, both this quantity here and here, these are constants of motion, of geodesic motion, and GTT. Sorry, I made a mistake here. This is GT phi. Both of these components only depend on the radial and theta coordinates. In principle, you can integrate this at least numerically, but you have reduced to first order equations. And a similar thing for the phi equation. You have the G phi, P phi plus GT phi PT. Okay. So these the T and phi equations are in some sense trivial because they are connected with killing vectors. The non-trivial part will be the radial and theta coordinates, which I'm going to focus now for a moment. So let me just write down now this capital R and capital theta. So capital R will be equal to R squared plus A squared minus AL squared minus delta. The Carter constant I mentioned, plus A minus L squared. So here I'm taking the energy normalized to 1 with no loss of generality. Also capital theta will be the Carter constant again, minus cosine squared theta minus A squared plus L squared sine squared theta, where this is the Carter constant, which is important to have this kind of framework. Okay, I hope that so far so good. So for the Kerr shadow, it will be important to understand what are called the spherical photon orbits that I mentioned in the beginning. Spherical photon orbits. Okay. So in Boyer-Lindquist coordinates, these will be orbits that have a constant radial coordinate. So radial coordinate R equals constant. Let me emphasize that this if you change the coordinate system, this statement might change. So this is not invariant. This is kind of connected. This radial coordinate is special because it's connected with the separability of the Hamilton-Jacobi equation. Okay. But nonetheless, there are generalizations of this concept, even in space-times that are not fully integrable. And instead of spherical photon orbits, there are other names, namely fundamental photon orbits, but essentially they play the same role. They can also determine the edge of the shadow of black holes as well. But then studying those orbits without using analytical tools is much more complicated, although it is possible. So let's focus on the Kerr's case, because then it's much easier to understand. So since we want null geodesics with constant radial coordinate, first we want to say that R dot is 0, but also that double R dot is equal to 0. So in a way, this is saying that the velocity, very naively speaking, that the velocity along the geodesic is 0, and also the acceleration is 0, so that you force the geodesic to always be at a constant radial coordinate. This implies that you have this capital R function to be equal to 0, and also the radial derivative be equal to 0. This gives some calculations, but combining both equations So combining both equations, we obtain the relation between the Carter constant for the spherical photon orbits and the angular momentum. You have 3r fourth plus a squared minus r squared, say r squared minus a squared. Okay. Now, if you take this relation and you put this back into the equation here for the derivative, you obtain the following relation. You obtain some function that can be a little bit long on the radial coordinate L squared plus some other function. I will not going to specify times the L constant plus some other function of the radial coordinate. So this is a quadratic equation. So this is a quadratic equation on the angular momentum. And so you can solve it. So you can obtain that L is minus B, whatever B is, B squared minus 4AC divided by 2A. And after you do extensive computations, this simplifies into L being equal to the mass r squared minus a squared plus minus r delta a r minus m. Okay. Now you have two roots that comes from the quadratic equation. So in principle, you have two sets of solutions. If you choose the plus sign, you get L plus is r squared plus a squared over a. And then taking this L and using this relation here that depends on L and nothing else, you obtain Q. So Q plus will be minus r to the fourth a squared, which is clearly negative, okay? And now I'm not going to prove this because this takes some time, but so you have to believe me that for spherical photon orbits, the Carter constant must be positive in order to have real motion in the theta coordinate, okay? So that means actually that this branch is not physical. It's never physical. It's not physical because the theta motion is not real. You'd get complex values. In a way, because the capital theta function, it will be negative. And if you remember, we had before a square root of that function. And so you have, everything is fine for the radial equation, but for the theta equation, you have a problem. And so that explains why this branch, the solution branch, is never physical. Now, that was for the minus sign, plus sign. For the minus sign, you get something a little bit longer, but so L minus will be minus r cubed plus a squared r plus m a squared minus 3mr squared a r minus m. And for the Carter constant, we have q minus cubed Okay, so these are going to be the physical orbits, at least a subset, because the capital Q here must also be positive. So there will be a range on the radial coordinate for which the Carter constant will be positive or equal to 0, cannot be negative. So these will define the photon region. The region in the radial an interval in the radial coordinates where these kind of spherical photon orbits are possible. So let me write that down, which is important. So to have spherical photon orbits, or SPOs for short, with real motion in the theta coordinate, then we must have that the Carter constant is never negative, so either equal to 0 or positive. So this defines this restricts the allowed range for the radial coordinate. In the Kerr case, it will be between some two values, R1 and R2. You can have exact expression for this, but I think that's beyond the point of today's lecture. So a typical plot of the function of the angular momentum function and the Carter constant function as a function of these radial coordinates. So it's just a typical plot of these two relations here that only depend on the radial coordinate with a fixed spin parameter will look something like this. So this is the radial coordinate. So the Carter constant will be 0 at 2 points, R1 and R2. We'll have typically a maximum, and the maximum will be always at 3m, okay, which is the location of the photon sphere for Schwarzschild, okay. So but it's in this case all the spherical photon orbits are kind of contracted in the single radius, but in the Kerr space the spin kind of breaks this degeneracy. So this is the Carter constant. And the angular momentum changes in some way like this, okay? Changes sign at some point. There is more to say about this, but I think for the moment, I think that this suffices. So let me just emphasize that the Carter constant at R1 and R2 is 0. And so this condition here above defines that the physical range for the spherical photon orbits is between these two extremes. Okay, let me also emphasize that for each radial coordinate, this gives the required L and Q in order to have a spherical photon orbit at that location. Okay, because this is a function of the radial coordinate, but for each radial coordinate that you choose, this just specifies, these functions just specify the values of the angular momentum and Carter constant in order to have an SPO exactly at that radial location. So let me show a plot in a moment. So let me break this for a moment. Share screen, desktop 2. Share. Okay, I hope you can see my screen. So you should be seeing a Mathematica file. Can you, I would kindly ask the chair to confirm, please.
Yes, we can see.
Okay, so this is, I'm going to share a link, a web link where you can actually play with this. Will be accessible for some time, not always, but feel free to use it to explore. So this is kind of a representation of a Kerr black hole. This in blue is the spherical photon orbit with the smallest radius. This is restricted to the equatorial plane. It is kind of the co-rotating light ring, co-rotating circular photon orbit. And as we increase the radius, you start to have some motion outside of the equatorial plane on surfaces with a constant radial coordinate. This is so let me do that again. And as you approach the pole, at some point it closes, and you can have some very interesting patterns, like so. At some point it closes over the poles. And then after you reach the poles where you have a zero angular momentum, it starts opening again, and now the angular momentum sign changes. So now it is counter-rotating these orbits. And as you approach R2, you have again an orbit restricted to the equatorial plane, but now counter-rotating. So this kind of collection of orbits that I've shown, it's a family of spherical photon orbits going from R1 to R2. Okay. Perhaps is there some very quick question, because I'm afraid I might be out of...
Yes, there are few, it seems. So the first question is how Hamilton-Jacobi approach exploits the fourth hidden symmetry. It's asked by Sanket Thakkar.
Yes, so this is a very nice discussion, but this would consume in its entirety at least one lecture. So I don't have time to show all the details, but essentially you have the Hamilton-Jacobi equation. You assume that you have some generating function, and you assume that that function can be separated into a radial and theta parts. And then by playing with the Hamilton-Jacobi equation, you can see for the Kerr case that you can separate all the radial dependency to one side of the equation and all the theta dependency to the other side. And so since this must be always true, then both sides must be equal to a constant. And so that's where the Carter constant appears, okay? This is connected actually to a more fundamental symmetry of the problem. I mentioned that the Kerr spacetime has two Killing vectors. It has also a trivial Killing tensor, which is the metric itself that gives the mass. But it also has a non-trivial Killing tensor of the second order that gives this Carter constant. So it's all connected to some hidden symmetries, which is not obvious at a priori. So this is just a very quick overview about the Hamilton-Jacobi formalism, but I don't have time, and unfortunately,
yeah, sure.
all the details.
So in this regard, there is another question. The Shayantan is asking whether is there any reference that deals with the detailed discussion on Carter constant? Is there any book or any review article?
Well, there are some reviews, of course, but I can recommend reading the original paper by Brandon Carter, perhaps. I think that would be a good place to start, perhaps. But actually, you can find plenty of discussions on this, also because that although these hidden symmetries is something very specific to Kerr, there are other spacetimes, other black hole spacetimes that similarly possess the symmetry. So it's not unique to Kerr as well.
Right. So another question is, could you please explain in detail why we consider the conserved quantities as E and L?
Well, yeah, so the conserved, well, it's just a name that you give them, but it has the nice interpretation that when if the photon arrives at spatial infinity, then you can compare with quantities that you are more familiar with, and then you can clearly see that E will be the energy of the photon at infinity, and L the angular momentum that an observer at infinity would see. And since these are constants of geodesic motion, you can always give that interpretation, okay? But these will actually might be different. For example, this energy might be different from an energy measured locally by some observer. It's always an energy with respect to an observer at infinity. But that is the reason, okay? So E for the energy and L for the angular momentum.
Right. So thank you. I think you can continue. There are no further questions at the moment.
Okay, thank you. So let me share my second camera again. Okay. So to observe a black hole shadow, we need an observation frame. So, so to observe a black hole shadow, we need an observation frame. Okay, so there are several frames of observation that you can choose. I'm going to focus on the ZAMO frame, which stands for a zero angular momentum observer. Okay. There's again a very detailed discussion about why this is an appropriate name, but I don't have enough time, I'm afraid. So just trust me on this. So this frame is defined by a set of basis vectors for the frame, which I'm going to write quickly as follows. Mm-hmm. They have omega, which is minus dt phi, g phi phi, and zeta is the square root of g phi phi, and then the determinant of the d phi sector of the metric. Okay, so this set of basis vectors, it satisfies a Minkowski type normalization norm, Minkowski-like norm. What I mean by that is that if you take the dot product between any two vectors, you get essentially a Minkowski type relation. So you have -1, 1, 1. Okay. So essentially, this basis defines the reference frame, kind of a laboratory. Could be a spaceship at some point in the space-time, not necessarily at infinity. Okay, but so this defines what a local observer would see. So let me make perhaps a drawing about this. So the ZAMO frame defines a reference lab frame, a local lab frame. So you have the black hole. Okay, it would be the black hole. And at some distance, you would have imagine a box, which it's kind of a local box. Okay, it's kind of your tiny box. It's where your spaceship is. And along one of the directions of the box, you have locally, you'd see this ER, you'd see this E theta and the E phi. Okay. So it's kind of an anchor where you can grab yourself to. And so you may ask, what's the interpretation of ET? So ET is essentially defines defines the local time frame. So defines the local time. So this would define essentially the local frame that you would see if you were in a spaceship with a zero angular momentum. So the momentum of a photon locally observed by the ZAMO frame, locally observed, is the projection of the form momentum p mu into the vector basis of the ZAMO frame. Okay. So in particular, you have the locally measured energy will be, so I'm assigning these parentheses to define locally measured quantities. This will be the time basis contracted with the form momentum of the photon. You have p theta, so the momentum in the theta kind of direction. These will be E theta mu, p mu. You have PR, which is E R mu p mu. and p phi okay. So if you because you have this kind of it's what you would expect to see in a local Minkowski frame, p mu will be minus m squared. This is 0 because it's a photon, and this will be minus pt squared plus capital P squared. Where this capital P squared is essentially the sum of this PR squared plus P theta squared P phi squared. Okay. Okay, so what can you do with this? You can define now an S2 sphere around the observer that defines the local sky. And at each point in your local sky, you can assign some observation angles, two observation angles, alpha and beta, okay? And then project your linear 3 momentum, which is this P essentially, in that along using those angles. You have PR is cosine beta, cosine alpha, P theta is P sine alpha, and then P phi is P sine beta cosine alpha, where alpha and beta are both kind of defined to be equal to 0 in the direction pointing to the black hole for convenience. So when you see an image, you are actually seeing a set of points in your local sky. So armed with kind of this framework, you can have a more precise definition for what a shadow of a black hole is. So let me write that down. So a shadow of a black hole is the set of points in the local sky that would receive or detect null geodesics coming from the black hole. So if you make backwards ray tracing, so if you trace the null geodesics backwards in time to see the origin of each one, the set of points in your local sky that would be coming from the horizon, then that's the shadow of the black hole. And since there is no radiation coming from the actual black hole, at least classically, then this means that the shadow is a dark region in the sky. So if you have an image parameterized by the angles alpha, beta, then the shadow is the set of points that would satisfy this condition. And then you can look at the edge of the shadow and try to find for the Kerr spacetime some analytical relation. So what is the condition for the shadow edge? So condition for the shadow edge. What is the condition? So consider a scattering of null geodesics. You have a black hole here. So this is the black hole. And you have some null geodesics that are coming from very far away, kind of parallel to each other. If the impact parameter is very low, the null geodesic will simply fall directly into the black hole. If you have an impact parameter which is large enough, so impact parameter is growing in this direction, the light ray might be bent but escapes the gravitational grip of the black hole. If it's slightly less, you can make some turns around the black hole. But if the impact parameter is just right, it will bend enough to kind of close over itself. And if the impact parameter is just slightly less than that, the geodesic will fall. So this is just a picture, of course. You can prove this more rigorous fashion. but the set of orbits, the set of orbits here in this scattering process that have the closest approach to the black hole in this scattering process are these spherical photon orbits, so orbits that have a constant radial coordinate. Okay, I hope at least this naive picture kind of helps understanding why. So these sets of impact parameters that would lead to light rays falling into the black hole, this will be kind of connected with the shadow. So these are actually geodesics falling into the black hole, but you can imagine the inverse process, so that these are actually geodesics being traced backwards in time, and then this kind of absorption cross-section is the shadow. So there is kind of somehow a relation between these two concepts. So the key point is that the edge of the shadow is determined by the spherical photon orbits we discussed before. So orbits that have a constant radial coordinate in Boyer-Lindquist coordinates. Now, if the black hole is very far away, sorry, before I mention this, let me mention something else. You can already relate several quantities. You can have PR is P cosine. This is for the Zemo frame. P theta is P sine alpha. You have P phi is P sine beta cosine alpha. You can use this to solve for beta and alpha. So we have beta, it's arctangent of P phi divided by PR. You have alpha, the angle alpha, which is arcsine of P theta divided by PT. And then you can also use the relations that we computed for the Zamo frame. So we have the locally measured energy is zeta E minus omega L. You have P theta, which is plus minus square root of capital theta divided by GTT. You have PR, which is capital R divided by delta GRR. And you have P phi L G phi. So here you have plus minus sign. This comes from the null geodesic equations as before. Here you only select the plus sign because you are interested only on outgoing photons, okay? In this kind of, you are looking at photons that are coming from the black hole's direction to observe the image. So here is only the plus sign that you are interested in. So if you now look at the case that where the black hole is very far away, so the black hole is very far away, so the angles alpha and beta will typically be very small and the radius will be very large, okay? So in this case, you have the alpha kind of simplifies to plus minus square root of capital theta divided by the square root of g theta theta 1 over zeta E minus omega L, and beta is L delta square root of G phi phi square root of R square root of G R R.
I think we have 5 minutes more.
Yes, I'm aware. Trying to speed up a little bit. So when you have the alpha and beta being very, very small, and also the radius very, very large, then you can obtain this very compact relation that alpha is approximately plus minus 1 over R square root of Q plus a square cosine of theta minus L squared tangent squared of theta, where this theta is the theta of the observer and R is the radius of the observer. And I'm setting, as before, E equals to 1. And beta is essentially minus L over sine theta over R. And you can see that this decays as 1 over r. So this kind of is expected, because when you have an object which is very far away, you would expect the observation angle of that object to decay as 1 over r. So you can define the impact parameters x as minus r beta and y as r alpha. And this has kind of a it has a well-defined limit for an observer that is very far away. So for the actual shadow of a black hole, essentially you take this expression and say that you can define the shadow edge of a black hole in a parametric way. It depends on the radius of the circle photon orbit as plus minus q r SPO plus a squared cosine theta minus L squared of, that depends on the radius of the SPO. And here is minus L, radius of the SPO, divided by sine of theta. So as before, you can use the relations of the Carter constant and angular momentum as a function of the radius of the SPO, of the radial circle photon orbit, between the interval between R1 and R2. So this relation defines in a parametric way the shadow of the Kerr black hole, which I'm going to show now. And since I'm essentially out of time, I think I might stop here. So just give me a moment. I'm going to stop this sharing and share my main screen. Yes, and then yeah. So I'm going to end with this. So this is kind of can you? So I would kindly ask the chair to confirm that you can see this.
Yes, we can.
Okay.
We can see it.
Thank you. So what I'm showing here is the shadow edge of the Kerr black hole in terms of the impact parameters, x and y, which is defined in this parametric way I just shown. Here on the right is kind of a depiction of the Kerr black hole, and this cone is kind of the observer where it is looking at. So by changing this theta, it's you can change the observer from the equatorial plane and approach the poles. Okay, in this case, for a very low spin, so this is the spin, very low spin, the shadow is always circular, or essentially circular. But when the observer is in the equatorial plane and you increase the spin, you can see that the shadow kind of tilts to the right and is becoming more and more deformed. Okay. And actually, when you reach extremality, there is a very characteristic kind of flattening on this left side. But of course, if you keeping the spin fixed, if you go to the axis, of course, because of axial symmetry, the shadow must become kind of a circle again, but with a different radius. Because if you decrease the spin, you can see that although the shadow is still circular, the shadow size can change a little bit. So the key point is, of course, in principle, by observing the shadow of an actual black hole, that there's of course a lot of technical details about what you can actually measure in terms of the shadow. But in principle, if you can measure the shadow of a black hole, you would be able to constrain some parameters of the black hole, namely the spin or some potential hair around the black hole. But for that, I would, of course, need more time, which I'm afraid I don't have. So I think since I'm out of time, I will stop here and address some questions that might have. So thank you very much for your time and attention.
Yeah, thank you, Pedro, for a very nice talk. Now the session is open for questions. So I would